Hello, this is Serene from Exam Help Lab. Today I'll be solving Chemistry PP2 AS Level Structured Questions 9701 PP2 variant 3 October November 2020. Question number 1. The graph shows the first ionization energies of some of the elements in group 2. Part A, write an equation for the first ionization energy of magnesium, includes state symbols. So first ionization energy is energy required to remove an electron from a gaseous neutral atom. So magnesium neutral atom in gaseous state loses an electron, becomes Mg plus in gaseous state, and an electron. Part B, explain the observed trend in first ionization energies down group 2. So first ionization energy decreases down group 2 because the size of the atoms increases as outer electrons get farther from nucleus due to increasing shielding, and thus the nuclear attraction, which is the force of attraction between valence electrons and nucleus, decreases. As a result, relatively less energy is required to remove an electron from an atom that's down in group 2 as compared to that which is on top of group 2. So we'll write that first ionization energy decreases down group 2 because outermost electrons get further from the nucleus, which increases atomic size and shielding increases. This results in decreased nuclear attraction, and as a result, relatively less energy is required to remove an outer electron from an atom that's down in group 2. Part C, the second ionization energy of beryllium is 1757 kilojoules per mole. Explain why the second ionization energy of beryllium is higher than the first ionization energy of beryllium. So beryllium's electronic configuration is 1s2, 2s2, and beryllium plus ion has a configuration of 1s2 and 2s1. And you must remember that metals have their ionic radii smaller than their atomic radii, which means when they are in ionic state, when they become ion, like Be, like beryllium plus ion, nuclear attraction is greater, being experienced by beryllium ion, and hence second ionization energy of beryllium gets higher than its first ionization energy. So we shall write that beryllium ion, which is Be plus, is a much smaller ion, and the electron being removed from the 2s subshell has greater nuclear attraction than the first electron being removed in the first ionization energy. So Be plus is a much smaller ion, and the second electron being removed has greater nuclear attraction. The ionic radii gets smaller than the atomic radii when metals lose their electrons because the amount of charge, the nuclear charge, increases on metal. That is the reason why the nuclear attraction between the outermost electrons of a metal atom and the nucleus, the force of attraction between them increases. Question number 2, phosphorus, sulfur, and chlorine can all react with oxygen to form oxides. Part A, phosphorus reacts with an excess of oxygen to form phosphorus 5 oxide. Write an equation to show the reaction of phosphorus with excess oxygen. So phosphorus exists as P4 molecule plus O2, that gives P4O10. 5 moles of oxygen gas. Part 2 is describe the reaction of phosphorus 5 oxide with water. So phosphorus 5 oxide reacts with water, and that gives us phosphoric acid, which is H3PO4. Now phosphorus 5 oxide is in a solid state, while phosphoric acid is in aqueous state, and it is acidic in nature. So this reaction would give us acidic solution, and the solid, which is P2O5 phosphorus 5 acid, that solid disappears. So we can write that solid disappears. And acidic solution forms. Part 3, state the structure and bonding of solid phosphorus 5 acid. So the structure is just simple molecular, and the bonding is covalent. Part B, the two most common oxides of sulfur are sulfur dioxide and sulfur trioxide. When sulfur dioxide dissolves in water, a small proportion of it reacts with water to form a weak bronzoluric acid. Part 1, explain the meaning of the term weak bronzoluric acid. So the term weak means something that partially dissociates into solution or ionizes the solution, and an acid is a substance that donates proton. So a weak acid would be substance that partially dissociates in solution and is a proton donor. Part 2, write an equation for the reaction of sulfur dioxide with water. So sulfur dioxide plus water, that gives us sulfurous acid, which is H2SO3. Part 3, sulfur dioxide reacts with nitrogen dioxide in the atmosphere to form sulfur trioxide and nitrogen monoxide. Nitrogen monoxide is then oxidized in air to form nitrogen dioxide. State the role of nitrogen dioxide in this two-stage process. So here nitrogen dioxide reduces to nitrogen monoxide, and this nitrogen dioxide is again regenerated, which indicates that nitrogen dioxide acts as a catalyst in this reaction. So this has a role of a catalyst. Part C, emissions of sulfur dioxide from coal-fired power stations can be reduced by mixing the coal with powdered limestone. Limestone is heated to form calcium oxide in reaction 1. This then reacts with sulfur dioxide and oxygen to form calcium sulfate in reaction 2. Part 1, state the type of reaction occurring in reaction 1. So calcium carbonate decomposes to calcium oxide and carbon dioxide. This is thermal decomposition. Part 2, use the data to calculate the enthalpy change of reaction 2. So reaction 2 is calcium oxide plus sulfur dioxide plus half moles of oxygen gas, which gives us calcium sulfate. Now that we are given the enthalpy change of formation values, we can only write all elements in their standard states down here, because that's how formation of all these substances is possible. So calcium in its standard state, plus oxygen gas in its standard state, as well as sulfur in its standard state. Now we don't have to forget balancing all these three parts. So calcium just 1 mole on all three sides, sulfur just 1 mole, and oxygen will be 4 moles, so we gotta add 2 here. Now for the formation of calcium oxide, we need calcium plus 2 moles of oxygen here to form calcium oxide. For the formation of sulfur dioxide, we have sulfur and oxygen in their standard states right over here. And for the formation of calcium sulfate, which is a solid, we require calcium, sulfur, and oxygen in their standard states to form calcium sulfate. Now we need to label all these arrows with their respective formation enthalpies. So 1 mole of calcium oxide will have an enthalpy of -635. 1 mole of sulfur dioxide will have an enthalpy of -297. And 1 mole of calcium sulfate solid will have negative 1434. Remember that the enthalpy formation of a gaseous atom will have a value of 0, and this is unknown to us. Now, enthalpy of direct route is going to be equal to enthalpy of indirect route. Direct route is reaching calcium sulfate right from its elements in its standard states, while the indirect one is reaching calcium sulfate but not directly from elements in their standard states, to calcium oxide and sulfur dioxide, and then calcium oxide, sulfur dioxide to calcium sulfate. So negative 1434 is equals to enthalpies of indirect route, which is negative 635, negative 297 plus X, and hence the enthalpy for the reaction 2 is negative 502 kilojoules per mole. Per D, chlorine forms several oxides including Cl2O, ClO2, and Cl2O6. Draw a dotted cross diagram of Cl2O, show out electrons only. So oxygen, we're gonna draw oxygen in the middle and chlorine on either sides. Oxygen will share one of its electrons with each chlorine atom, and chlorine will also be sharing one electron with oxygen atom. Part 2, ClO2 can be prepared by reacting NaClO2 with chlorine. Write the oxidation state of chlorine in each species in the boxes provided. So here chlorine exists as a molecule, so it has an oxidation state of 0. Here oxygen has an oxidation state of -2, hence chlorine will have an oxidation state of +4. Here as chlorine will have an oxidation state of -1. Part 3, Cl2O6 is produced by the reaction of ClO2 with O3. The reaction takes place at 500 Kelvin of temperature and 100 kilopascals of pressure. State and explain the effect on the yield of Cl2O6, which is a product, when the experiment is carried out at 1000 kelvins and 100 kPa of pressure. Now, if we increase the temperature from 500 kelvins to 1000, that's a double, and keep the pressure constant, equilibrium will shift to the side, which decreases the temperature. And in this case, in this reaction, it's the backward reaction, that's endothermic reaction, which decreases the temperature. So the yield of Cl2O6 will decrease because the equilibrium will shift towards the left. So we can write that yield of Cl2O6 decreases because increasing the temperature will shift the equilibrium to the left. Because equilibrium shifts towards the left, and forward reaction is our exothermic. Now, we have to state and explain the effect on the yield of Cl2O6 when the experiment is carried out at 500 kelvins and 500 kPa of pressure. Increasing pressure would shift equilibrium to the side, which has fewer moles of gases, so equilibrium will shift towards the right and yield of Cl2O6 will increase. So we'll write that yield of Cl2O6 increases because there are fewer moles of gas on the reactant side. We have 3 moles over here and we have 4 moles on the reactant side. So yield of Cl2O increases because equilibrium shifts to the right, which has fewer gaseous moles. Part E, element E is a period 5 element. You can consider period 3 elements in this part of the question instead of going out for period 5 elements. So E reacts with oxygen to form an insoluble white oxide that has a melting point of 1910 degrees Celsius. The oxide of E conducts electricity only when liquid. Okay, so the oxide of E conducts electricity only when it's in molten state. Therefore, we can say that E forms a metal oxide, and it could be either sodium oxide or magnesium oxide or aluminium oxide. And these are the only oxides from period 3 that can conduct electricity when they're in their molten state. And they also share this property that they have high melting point. So we can say that element E forms a metallic oxide. So it could be either sodium, magnesium, or aluminium. E also reacts readily with chlorine gas to form a white solid that reacts exothermically with water. Okay, so chloride of E reacts exothermically with water, meaning the chloride doesn't dissolve into water. It instead hydrolyzes. This is also confirmed later when it says that a white PPT forms when the resulting solution reacts with silver nitrate, and that PPT dissolves in dilute ammonia. So I can say that E's oxide has ionic bonding because ionic compounds conduct electricity when they are in molten state only, and that's because at that state they have ions that are free to move and conduct electricity, which the next part is asking us to mention. Suggest the type of bonding shown by the oxide of E. Explain your answer. So E has a metal oxide, thus it has ionic bonding. And we can reason this is statement because it says that it conducts electricity only when it's in liquid state. So we can write that because it conducts electricity in molten state when ions are free to move and conduct. Part 2 suggests the type of bonding shown by the chloride of E. Okay, so chlorides of sodium and magnesium are the only ones that dissolve in water. They do not hydrolyze into water and form HCl. Rest of period 3 elements will get hydrolyzed into water, like aluminium, silicon, and rest of it, and phosphorus, which have covalent bonding with chloride and iron. And we came onto this conclusion because it's said right over here that chloride of E hydrolyzes into water. It reacts exothermically with water. This statement that it reacts exothermically with water, this means that it hydrolyzes into water. It could be either aluminium, silicon, phosphorus, or sulfur. So these are all the elements that when form form a bonding with chloride, they form covalent bonding. So it's either AlCl3 or SiCl4, PCl5. They all share covalent bonding. So we can write that the type of bonding with the chloride of element E is covalent bonding. And reasoning to that is because the chloride of E hydrolyzes in water. Question number 3, the reducing agent LiAlH4 can be synthesized by reacting aluminium chloride with lithium hydride. At 200 degrees Celsius, aluminium chloride exists as Al2Cl6. Draw the structure of Al2Cl6, showing fully on any coordinate bonds in the molecule. So Al2Cl6 has covalent as well as dative bonding. There is this Al that shares each of its 3 electrons with 3 chlorine atoms, while all these 3 chlorine have their 3 lone pair of electrons. This lone pair of electrons from this chlorine will be forming a dative bond with another aluminium atom, which shares each of its 3 electrons with other 3 chlorine atoms. Now this electron of aluminium will be shared with another chlorine atom that has 3 lone pairs of electrons. Now this pair of electron of this chlorine atom will be shared with this aluminium atom, and this is how dative bonding forms. while the other chlorine atoms will have their lone pairs not being shared. So these were showing the outermost electrons. Now we will show them their bonds. So this aluminium atoms forms covalent bonding with these two and this one too, while this one will have a dative bond with the other aluminium atom. This aluminium atom is attached to a chlorine atom over here, and this forms a dative bond with this aluminium atom. The rest of chlorines on this aluminium will only be forming covalent bonds. Part 2, at 1000 degrees Celsius, aluminium chloride exists as AlCl3. State the bond angle in AlCl3. So aluminium, after sharing all its electron with these three chlorine atoms, will not be having any lone pair of electrons left, so it would be 120 degrees. Part 3, lithium hydride contains the ions Li plus and H minus. State the electronic configuration of these two ions. So electronic configuration of a neutral lithium atom would be 1s2 and 2s1. When we take away an electron, it becomes only 1s2. Now, hydrogen has its electronic configuration of 1s1. When an extra electron is added to it, gets a complete shell, so it gets 1s2. Part 4, LiAlH4 decomposes slowly to form LiAl and hydrogen gas. LiAl shows metallic bonding. Describe metallic bonding. So metallic bonding is all positive metal ions surrounded by cloud of delocalized electrons. Part B, LiAlH4 cannot be used in aqueous solution because it reacts with water to form LiOH. So LiAlH4 reacts with water to form lithium hydroxide plus hydrogen and a white precipitate which is soluble in aqueous sodium hydroxide. So this could be aluminium hydroxide. Identify the white precipitate, so it's aluminium hydroxide. Part C2, students try to prepare 2-hydroxybutonic acid. In the laboratory, both students oxidize butane 1,2-diol to form P in reaction 1. One student then reduces P using LiAlH4, Q is formed. The other student reduces P using NaBH4, R is formed. Part 1, state the reagents and conditions required for reaction 1. So reaction 1 is secondary and primary alcohol being oxidized to ketone and carboxylic acid group. So this requires acidified chromate ion and heat under reflux. Acidified chromate ion or potassium dichromate, which is K2Cr2O7, and heat under reflux. Part 2, only one of the students successfully prepares 2-hydroxybutanoic acid. Identify which of Q or R is 2-hydroxybutanoic acid and explain the difference between reactions 2 and 3. Okay, so now at first you should know among LiAlH4 and NaBH4 which one has more reducing power. It's actually LiAlH4 which is stronger and can reduce both acids and ketones, but NaBH4 can only reduce ketones back into secondary alcohols, not acids to primary alcohol. The desired product, which is 2-hydroxybutanoic acid, has both carboxylic acid group and secondary alcohol group. So reaction 3 would be correct to get 2-hydroxybutanoic acid. And so we can write that R is 2-hydroxybutanoic acid. Because NaBH4 only reduces ketone group, while LiAlH4 has the ability to reduce both ketone group and the carboxylic acid group. A third student prepares 2-hydroxybutanoic acid using propanol as the starting material. In step 1, the student reacts propanol with a mixture of NaCN and HCN. Part 3, draw the mechanism for the reaction of propanol with the mixture of NaCN and HCN to form S. Now C2O double bond will break heterolytically. C gets a partial positive charge and O gets a partial negative charge. an arrowhead towards O, and Cn minus with a lone pair of electrons from the catalyst NaCN gets attracted towards this carbon with a partial positive charge. Now the next, which is the intermediate product, will have Cn attached to it, and an O with a lone pair of electrons and a negative charge, which will be attracted towards H plus from HCN. Part 4, complete the equation for the reaction step 2 when S is heated under reflux with HCl. So this is heated with HCl and water. The CN group turns to carboxylic acid group and we are left with NH4Cl. Now we need to balance our equation, so we must add 2 over here to balance our hydrogen atoms. Part 5, the infrared spectrum of an organic compound is shown. The organic compound is either S or 2-hydroxybutanoic acid. Deduce the identity of the compound, give 2 reasons for your answer. So structure S has OH group, the nitrile group, and CH groups, while 2-hydroxybutanoic acid has CH groups, the hydroxyl group, and the carboxylic acid group. Okay, so there is a weak peak at around 2200 to 2300 per centimeters. There is a peak at around 2800 to 2950 per centimeter, and there is a strong peak over here which is beyond 3000 per centimeter. Now when you try matching these absorptions with values in your data booklet, you will know that this infrared spectrum is of compound S, because there is an absorption due to nitrile group, and also because there is no absorption due to COOH group, which should be between 2500 to 3000 per centimeter. There should be a strong peak due to COOH group, but since this peak is not present in the infrared spectrum, we are going to conclude that this infrared spectrum is of compound S. So we'll write compound S. And we gotta give 2 reasons for our answer. Now, compound S because there is absorption due to nitrile group at around 2200 to 2250 per centimeters. So if it was 2-hydroxybutanoic acid, it should have got a strong peak at around 2500 to 3000 per centimeter. So there is no absorption at around 2500 to 3000 per centimeter, which is due to carboxylic acid group. Question number 4, iodine is used in many inorganic and organic reactions. State and explain the trend in volatility of the halogens from chlorine to iodine. So volatility decreases from chlorine to iodine because of increasing number of electrons that strengthen the intermolecular forces or the van der Waals forces in the molecules of halogens. Part 2, explain why HI is the least thermally stable of HCl, HBr, and HI. So HI has got the lowest bond enthalpy or energy required to break the bond. That's why it requires least temperature to break the bond. Part 3, the table shows the electronegativity values for hydrogen, fluorine, and iodine. Explain in terms of intermolecular forces why HI has a lower boiling point than HF. So HF and HI both are polar molecules, but the greater the difference between the electronegativity values of elements in a bonding, which is HI and HF, the stronger that bonding will be. Here HF has a difference of 4 minus 2.1, which is 1.9. HI has a difference of just 0.4. Hence, the intermolecular forces present in HI are weaker than that in HF. So we can write that intermolecular forces of HI are weaker than that of HF. And also because HF has permanent dipoles and HI has induced dipoles, which are weak in terms of intermolecular forces. Part 4, iodine reacts with hot concentrated aqueous sodium hydroxide in the same way as chlorine. Write an equation for the reaction of iodine and hot aqueous sodium hydroxide. So just like chlorine, iodine plus hot NaOH gives NaI. With chlorine, it would form NaCl, NaClO3, and water. So it would be NaI plus NaIO3 plus water. And we will have to balance our equations. So 3 moles of iodine, 6 moles of NaOH, 5 moles of sodium iodide, 1 mole of NaIO3, and 3 moles of water molecules. Part B, iodoalkenes contain carbon-iodine bonds. The simplest iodoalkane is CH3I. CH3I can be made from methanol. Identify a reagent that can convert methanol to CH3I. So to convert alcohol to halogenoalkane, we can use HCl, HI. So to convert OH to I, we can have HI gas. Part 2, 1,2-diiodoethane can be made by bubbling ethene into liquid iodine. Fully name the type of mechanism shown in this reaction. Okay, so converting alkene to halogenoalkane, we can have this type of mechanism is called electrophilic addition reaction. Because there's addition of 2 iodine atoms. Part C, J reacts with NaOH forming different products depending on the conditions being used. Part 1, name J. So this is a methyl group, this is a carbon atom, and this is again a methyl group and 2 ethyl groups. So a methyl group and iodine attached to the second carbon atom, so 2-iodo, 2-methyl butane. Part 2, J reacts with NaOH to form K. Fully name the mechanism of the reaction of J with NaOH to form K. So NaOH has got OH with a negative sign and a lone pair of electron, which is a nucleophile. So this is nucleophilic substitution reaction. Part 3, J reacts with NaOH dissolved in ethanol to form a mixture of 2 alkenes, L and M. Alkene L is shown in the box provided. Draw the structure of M. Now this iodine atom will be removed, and this leaves the double bond to settle between either the first and the second carbon atom or the second and the third carbon atom. L has got the double bond between second and third carbon atom. Hence, M will have the double bond between first and second carbon atom. So this is the double bond, and we have a methyl group on the second carbon atom and an ethyl group. Part 4, explain why L does not show geometrical isomerism. That's because this carbon atom, which is carbon-to-carbon double bond, is attached to 2 methyl groups. And for cis-trans isomerism to show up, you must have each carbon atom of carbon-to-carbon double bond to attach to 2 different atoms or group of atoms. Since this carbon atom of carbon-to-carbon double bond is attached to 2 same methyl groups, hence structure L doesn't show geometrical isomerism. you can write that a carbon of carbon to carbon double bond is attached to two methyl groups. Part 5, L reacts with hot concentrated acidified KMnO4 to form propanone and one other organic product. Identify the other organic product. So this carbon atom will turn to carboxylic acid group, hence it would become COOH, and there is a methyl group attached to this carbon atom which stays same. So this would produce ethanoic acid. Part 6, propanone reacts with excess alkaline aqueous iodine. Complete and balanced equation for this reaction. So ketone reacting with alkaline aqueous iodine will give us triiodomethane, which has a formula of CHI3. Now balancing we'll have 3 moles of iodine here, 4 moles of hydroxide ion, which is NaOH, 1 mole of this anion, 3 moles of water molecule, and 3 moles of iodide ion. Part 7 state one observation that can be made in the reaction in C. Part 6, that's yellow precipitate, which is due to triiodomethane, so yellow precipitate. So that was the end of the paper. Thank you for watching.